So time for exercises. First of all, I'll show you a couple of slides with examples of R code. You already remember how to make a scatter plot. I also introduced you these MDA tools, plotting functionalities when you can also colorize points. But this is how to add a baseline fit. So if you want to show the baseline fit for your X and Y values, that's the way how to do that. And this is how to calculate a covariance in R. Even if you calculate covariance for two variables, that's just a property of R function co. It computed as a covariance matrix, so we'll get 2 by 2 matrix like I showed you today. You can also apply this function to a matrix, and it will compute a covariance matrix for all columns of your matrix. If you compute correlation for X and Y, you will get one value. So in this case, core doesn't return a matrix, it returns one value, correlation between X and Y. But if you compute core, if you apply core to a data matrix or data frame, then you will get also a correlation matrix. So you will get as many correlation coefficients, as many combinations of all your columns you have, right? And then this is how to make a heat map if you have a correlation. First of all, you need to install a package. There are many different packages that allows you to make a heat map. I use this package in my examples, heat map. It's not necessary to use this one. You can find another one. Then this is how to compute correlation. You can see that I already have people data. It's my matrix with people data. And then if I apply function core to this people data, I get a correlation matrix. And this is like extra things I want to do. I just specify how many colors I want to use. I say I want to use 100 colors. And then I specify the smallest value will be -1. And that will be, for example, blue color. The largest value should be +1 and will be, for example, red color. The colors depends on the color palette we use. And then how many values in between, including these two. So we'll have 100 values between -1 and +1, both included. And then I will simply make a heat map. I say, okay, use R, the correlation matrix for the heat map. Then do not scale the data. Use it as is because it's already scaled. Then cluster columns and rows. This is what you need to combine this, make these clusters, nice clusters here. So I say clusters, cluster columns and cluster rows. It's not necessary, but it makes this nice representation. Okay. Then this is a funny thing. It's not necessary to use it, but if you do not use these two parameters, then you will see the tree of clustering. So you will see, okay, this is one tree, then you have another tree, and then you have like this. Okay, so to avoid these trees and then to save some space, I simply specify the tree height. The height of this tree should be 0 for rows, and the height of this tree should be 0 for the columns. It's not necessary once again. And then that's it. That's actually it. And I think I forgot to specify the breaks, but I'll do it in my code later in RStudio. Okay, so this is how to create a correlation map. Now let's go to RStudio and play with people data. So I will reproduce everything, make different scatter plots, add line fits, compute correlations, and so on. Well, first of all, we need to load the people data. I actually have people data as Excel file, but since we already learned a little bit about MDA tools, it will be easier if we just load data from MDA tools, because then we don't need to change the names and so on, prepare the data. So I will just load the MDA tools. Run it, and then I can just say data people. So MDA tools has this data set sort of built in, and then you can see that by default it's a matrix 32 by 12, and then you can see that it already has the names of the persons and also the names of the variables, right? So we don't need to do anything else. And then let me start with creating simple plots, like for example I create a couple of plots. And then also show you how to add this baseline fit for these plots. Okay, so first of all, I will take the height and weight separately. I will say height, take people from the first column of this data matrix, people, and then weight, it's the second column of this data matrix, people. And then I will simply make a plot. I say plot, and then I'll just write height and weight with a comma. Then I will make it a blue color. So this is just a simple way to make a box, the scatter plot, right? And then if I want to add, for example, this baseline fit, I need to make a linear regression model. And to make a linear regression model, in R there is a function, and then you specify your Y values, its weight, then you write a little relationship symbol, this little tilde wave and then the x values. Yeah, but in this case you will get a model. You can make a plot for this model if you use function abline. It will simply take the intercept and slope of this model, and then it will use the intercept and slope for showing a line. And that's how it looks like, right? And of course, since it's just a plot, you can change the, for example, the color. Let me use gray color, for example, and then you can change the line type, for example, and then that's how it looks like. More or less the same as I have shown you in my slides, right? So that's relatively simple. Now let's talk about covariance and correlation. And you remember that covariance, we can compute covariance by just applying a function co. Wait, yeah. You remember that I told you in the videos, in the lectures, that it returns a matrix, but apparently it doesn't anymore. I mean, I think that in some versions of R it returned a matrix, but now it returns also one value, only one value. Okay, and then apparently if you compute the covariance between weight and height, then you will get the same value, right? And then covariance computed between weight and weight is just a variance of weight. How we can prove that? We can compute standard deviation of weight and square it, right? So remember that variance is a squared standard deviation, and you can see it's identical numbers, right? And then if you want to compute a covariance matrix, you can just simply take, let me use a subset, let's say first three variables only, first three columns of the people data. I say, for example, the covariance matrix is just covariance, and then for matrix people, and then only first three columns, right? And then you can see that that's the covariance matrix. And then you can see that it's 3 by 3. Apparently, the diagonal value is the variance. You remember that variance for weight is 230, and that's exactly what we have here. Then you can see it's also symmetric, right? So this value is the same as this value, right? Okay, and then you remember that we can actually compute the variance covariance matrix manually if we mean center data first, and then we just take a cross product of the mean centered matrix. Let me do that as well. So well, first of all, I will mean center data. I will use xm to denote the mean centered data. And in R, there is a function that does actually, it can standardize your values, but we need only mean centering. You can see that function scale has 3 arguments, your original data matrix, then center to true, scale to true. And by default, it's actually standardized every column of your data, but I need to only to center it. So I will just simply write scale equal to false. So I'll say people, then center is true. I can skip it because it's a default value, and scale equal to false. So in this case, xm will be, let me use only first 3 columns, okay? First 3 columns here. And then I will show a head of xm. So if I run this code now, you can see that now I have a mean center data. How we see that? We can simply compute, for example, we can compute mean of height and weight values, people to mean. So you can see that, for example, the mean of height is 173 centimeters. And then in centered data, Lars has a height 24.8. What it means? It means it's 24.8 centimeters larger than the mean. So if you sum up this value and this value, you can see it's approximately 198. And you can see indeed Lars is a first person in this data, so it's easy to see it. So if you look at the first row, you can see that indeed Lars has a height 198, right? So I will just remove this one. So xm in this case, because I apply scale on his center true and scale false, it's just means the original data but mean centered. So the mean of every column is 0, right? Now I can compute the covariance matrix. I will use C2. It's like a manual covariance matrix. And then what do I need to do? First of all, I need to take this cross product. And you remember there is a function cross prod. There are 2 functions, cross prod and cross prod t. What's the difference between them? I'll just write a comment here. Cross prod assumes that it's x transposed x. And then cross prod t cross prod, it assumes it's x transpose. That's the one we use for the spectral data, right? So it depends at which matrix you want to transpose, the first and the second, right? So I need to transpose the first matrix, so I just use cross product, and then I say xm, and I just don't need to write it twice because it assumes if it's just one argument, it should do it like this. And then you remember I also need to divide to the number of degrees of freedom. I have its number of rows in xm minus 1. Then I should, this cm and c2 should be identical. Let me just compute it first and then show you c2, then show you cm, so you can see both, and you can see that they indeed and they identical, right? So strictly speaking, covariance matrix can be computed just by taking a cross product of mean-centered data matrix and divide to the degrees of freedom. Okay. Once again, it's not very often you use covariance, only if you developed different algorithms. For example, principal component analysis, we use covariance and principal component analysis. But it's nice to know what covariance is, because actually the next point, the next statistic we are going to talk about, correlation, is actually based on covariance, right? So correlation, as I said, correlation, you can compute correlation by using just height and weight, by using function core. Then you can see that's the correlation, 0.96, right? You remember you can actually compute covariance for height and weight, yeah? And then you can divide to standard deviation of height times standard deviation of weight, and that will be also the correlation, right? So let's check if it's true indeed, and we get the same value, and as you can see, it's absolutely identical, right? And then sometimes you need also to make a correlation test and, for example, compute a confidence interval for the correlation. I hope you remember the idea of confidence intervals from statistics. In this case, in R, you can use core test for that, height and weight. And then you can see that you got the correlation coefficient, but you also got a confidence interval. So it means that, I mean, if you take another 32 persons from this population, the correlation coefficient with 95% confidence will lie in between. You can see that even the smallest boundary, the lower boundary of the confidence interval, is pretty high. So the correlation is indeed high. And that's the p-value. Here we assume that there is no correlation in population. And then you can see it's strictly speaking, it's impossible to get the data that we have if there is no correlation between height and weight from the population. Okay. So that's how to calculate correlation coefficient. And I must say that the correlation we discussed in this course is called a Pearson correlation coefficient. You can also use some other ways to compute correlation. You can Google like different correlation coefficients like Spearman correlation and some others. But like a Pearson correlation coefficient, the default one is sort of the most widespread. Okay. Then the correlation matrix, it's the similar thing. You can just apply core to people. Let me now first apply to the first 3 columns, and then I will also do it for all people. So that's how to do it. And then if you look at the R, you can see that the matrix is similar to covariance matrix, but now it's bounded by -1 + 1. And then you can see that, of course, correlation of height with height is 1 because it's the same value, so they lie on a straight line. But you can see that the correlation, here we have hair length. Strictly speaking, we shouldn't compute correlation with hair length because hair length is just a binary variable. But let me just do it anyway here, just to make it simple. And then you can see all the correlation coefficients here. And then if you have 3 by 3, if you have only 3 variables, it looks pretty fine. But of course, if you have many variables, so let me just compute the correlation matrix for all people data. You can see that it's pretty huge. Yeah, it's a lot of data, and it's very difficult to spot any patterns in this number. So we have like 144 numbers here. Yeah. So in this case, the good idea is to use these heat maps. And actually, there are many ways to make a heat map. So for example, there is a function image in R, and then you can use it to make a heat map. You can see that's the heat map, and then you can see this is the columns, this is the rows, for example, and then you can see some also color gradients. But the problem with image is that you actually don't see what color is what. You can't add this color gradient, you can't organize your variables in a nice way. So therefore, I recommend you to use one of the packages that produces the real heat maps. And one of them is just p-heatmap. Let's install it. I don't have it yet here. So p-heatmap. Yes, you remember that you need to run it only once, and then you just remove this. So I wait a little, and then while I'm waiting, I will just write the next command to load this pheatmap package. So it's almost done. So now I can use it. So now I simply write run pheatmap, and then by default I can just write pheatmap, and then R, right? So that's the default value. And you can see by default it's actually cluster all my rows and columns. That's the default option. So we see the same clusters that I have shown you before. And it also shows the gradient, automatically define all colors, automatically define the range. You can see, for example, -1 is absent here because we don't have in my data -1. And it also shows this how it's actually combined this together. So you can say this is the first cluster, then this together with beer, it's the second cluster, then this is a separate cluster, separate cluster, separate cluster, and so on. So it shows also the tree, how to cluster the variables, right? You can change this. First of all, you can, for example, make breaks manual. For example, you can say breaks. It's a sequence. It starts from -1, it ends with 1, and then the length of this sequence, how many values you have in between, is, for example, 100, right? So in this case, if you look at the breaks, you can see it's a vector with 100 values that equally distanced from each other, from -1, and then you can see up to +1. And then you can provide these breaks to your pheatmap function. So you simply write breaks equal to breaks. And then you can see now what's the difference is that now you have -1 here, and then you have 100 colors between -1 and 1, and then this is adjusted accordingly, right? Then if you don't like these trees, you can skip them. In this case, you need to provide height values for the tree for rows. For example, 0. Let me just use this one, and then you can see that for rows it disappears, right? So I said this, the height of this tree is 0, so it means it's nothing, right? And then I can do the same for columns. Tree height columns 0. Yeah. Then you can see this also disappeared. And then what else I can do? I can skip the clustering. So I can say don't cluster. And then the position of the rows and the columns will be the same as in the original matrix. Okay, let me just show you that. Let me just use it somewhere here. And then this cluster, it's called cluster rows, false, and then cluster columns also false. Okay. So in this case, you can see that it doesn't cluster, so we don't see this cluster very clearly anymore. But we have the same order, right? So height, weight, hair length, and so on. And we still see that first 4 are very well clustered. Then this one, it's beer, and then these 2, you can see swim and region. You still see this cluster sort of, but not as clear as if you cluster the variables, right? So if you make it, cluster it, you can see that the representation is much easier. Okay. So that's actually it. And the next learning sequence will be relatively large, where we are going to talk about all main details of principal component analysis. And then we will find out that PCA can also reveal these clusters, but actually PCA will provide you much more information also about the nature of these clusters. So see you in the next learning sequence.